Okay, so we have 3 more classes. I'll talk about numerical differentiation and integration today and into Wednesday, and then we'll do a little bit with graphics. And I had a note on Piazza saying that the graphics unit is really long, and that's mainly just because I had a bunch of material already prepared, so I figured I'd just provide it to you if you do want to look at it. We'll just hit a couple highlights in terms of the material that's in the graphics unit. Okay, any questions before I get started? Okay, so the last thing I wanted to do just to finish off, or the first thing I wanted to do to finish off the optimization unit was just show an example of doing optimization with constraints in R. And before I say that, I'll just say that R is a bit limited in terms of dealing with convex optimization. So if you're really getting sort of seriously into convex optimization, you might want to look into either Python has this package called cvx-opt, and MATLAB has a function called fminCon, and also some sort of system for doing convex optimization. I think the two of these might be related. I think there may be some more general software package that both of those are hooking into. Obviously I don't know the details off the top of my head. So those are both options that are out there. But just to show you a little of what's available in R, I'm taking this function called the Rosenbrock banana function, which is just this function here. Oops. On this line here. And if we plot that, it looks like this. So it's a bit of a complicated, it's only 2 dimensions, but in some ways it's a little bit of a complicated function to optimize. And if we want to do that in R, so here's the gradient explicitly computed analytically. And then I have code where I'm just doing the plotting, so I need to source all this. Okay. Okay, so the idea is that R is not quite as general as we might hope. R will handle linear inequality constraints, but not general functions H. So we've been saying things like we might have some set of constraints, say h of xi is less than or equal to 0. And so R is not going to handle general functions H, but it will handle linear functions. So this is basically the form that we need to get our constraints into. And if we have less than or equal to, well, we can just take a minus. If we have a constant, we can subtract that off. So you basically need to be able to write your constraints like this, where here theta is playing the role of what we've often been calling x. So this is going to be a matrix with each row indicating what that constraint is, and then the CI, the corresponding CI. Okay, so in this case, suppose that I wanted to constrain things such that I have 2 constraints here. I want to say x1 is less than or equal to 0.9, and then x2 is less than or equal to x1 plus 0.1. So if you just monkey around with the arithmetic, you can see that I can write that as this matrix UI, where the first row corresponds to the first constraint, and the second row corresponds to the second constraint, and then the CI are these constants. And the minus 0.1 comes in here because of the fact that I'm having to put it in this form of the UI times theta minus CI is bigger than or equal to 0, and so you end up having some negatives come into the picture. Okay, so then what R is going to do is, remember last time we talked about the idea of the barrier function. So we had our original f of x, and then I want to move the inequality into the objective function. And so if I did that, the actual function that I would move into the objective function would suppose that suppose the inequality is my x has to be less than some cut point here. Let's call that C. So I could just include this function as f of x plus this function here, but then this isn't smooth, so the idea is we put in this approximation where we put in this logarithmic barrier function that looks like this, and then we slowly let this function get closer and closer to looking like the actual inequality constraint function here. So R does actually do that. R doesn't actually require that the functions be, that the function f be convex. So the idea is what's going to happen here is we're going to, okay, so here I'm just plotting the constraint regions there, and now I'm going to do the constraint optimization. So I have to give it a starting point here, and as you might expect, that starting point has to be in the feasible region. It has to satisfy the constraints, so we have to be somewhere in that region. And I'm going to give it the actual function and the gradient function that I previously defined, and I'm going to give it the ui and the ci. And it's going to go through this procedure of starting off with some value of t, which it calls, in its syntax it has mu, which is 1 over t, but we had written it as t in the notes and talked about it that way last time. R is going to start out by optimizing f plus something that looks like this. We're going to find the best point given that. Then at the next iteration, it's going to make this a little bit steeper here. It's then going to use the value from the first iteration as the starting point for the second iteration and go through and optimize with the new second barrier function, and then it's going to slowly work its way up till the barrier function more or less looks like the actual constraint. So you can imagine this has the iterations over mu or t, depending on how we look at it, and embedded within each of those we're doing an optimization. So it's going to be more time consuming than just our standard optimization where we do the, it's got a loop nested within a loop. In this case, it looks like it didn't take very long, but you will see examples where it does. What the hell? I just hit some keys that pasted in something from a long, long time ago, apparently. All right, hopefully that did not erase what I had before. Okay, so it found, I guess I need to go up and replot. Okay, I'm having all sorts of problems here. Okay, there we go. Okay, so I had set up the constraints such that I was below this line and to the left of this line here, and it's maybe a little bit hard to see if you're particularly if you're in the back. But basically, it found an optimum point that was right here, which is on this line here, but a little bit below this line here. So it does seem like it's doing what we wanted it to do. And this was it was just to indicate that was this region here was the feasible region defined by the combination of the two constraints. And you can play around with this. I just have another example where I constructed a different feasible region. Here, x1 is less than or equal to 0.9, so that same vertical line, but now x2 has to be bigger than or equal to x1 plus 0.1. So now we're going to be up in this region here. And if we give it a point, if I forget to change the initial value, this point is no longer going to be in the feasible region, so it's going to give me an error. It says that the initial value is not in the interior of the feasible region. So I have to change what my initial point is, so now I'm changing it from 0.5 and 0 to the -3 and 2. And now if I do it, that should work. And now it found this new point here. So this was our feasible region. I had -3 and 2, so I guess I started out here, and it ended up finding that the minimum value was here, which is not on the boundary with respect to this point, but is on the boundary with respect to this guy, this one of the constraints there. Okay, so any questions about that? All right, So I did try. I did think I could be a little bit clever and say, what about if I wanted to optimize with an equality constraint? So what if I want to optimize such that x1 minus x2 is exactly equal to 0.1, which would be along this line here. And so mathematically, one of the standard things you could do is say, well, that's equivalent to two inequality constraints. That's equivalent to x1 minus x2 is less than or equal to 0.1, and to x1 minus x2 is greater than or equal to 0.1. So I thought, well, maybe I can put those two constraints in and get it to do the minimization along the line. Turned out I was trying to be a little bit too clever for my own good, apparently, because whatever I did in terms of giving it an initial value, it wouldn't accept the initial value. So I was trying to give it an initial value that would be along this line, and that didn't work. So you might be able to guess why that is. If I'm trying to put in both of these at once, and then I give it these 2 points, well, we know these 2 points are separated by 0.1, so they actually satisfy being on that line. But think about what might happen if I now try and check either of both of those conditions in R. I'm going to check that x1 minus x2, that the difference is less than or equal to 0.1. It's either going to be true or false, but because of the numerical issues in representing 3.0 and 3.1, it's not actually, it's going to be a little bit on one side of 0.1 or on the other side of 0.1 when it's actually evaluated numerically. So I think what's going on is it's failing in one of these checks is turning out to be true numerically, and the other check is turning out to be false numerically. Yeah.
Could you just add a machine epsilon to your inequality?
Say more what you mean by that.
So we're saying that 3.1 and 3.0 aren't exactly represented as those numbers in the computer, and so maybe adding some sort of epsilon or some sort of degree of freedom might get you not an exact answer, but an approximate answer.
So do you mean like basically making the line a little bit wider? Is that
kind of like that, yeah.
Okay, so that was actually where I was going to go with this, which is what I ended up playing around with, which is suppose we make the constraint not that you have to be exactly on the line, but you have to be within a little bit of a tolerance of the line, which I think is along the lines of what you're suggesting. So I did actually do that, and I played around with it a little bit. So this was me with my little epsilon here, which here it looks like my little epsilon is 0.001 within plus or minus that of the line. And now if I do this, I'm actually forgetting why. So it looks like I took out the gradient here. I wrote this code a week or two ago, and I've now actually forgotten what the. Oh, okay, yeah. So for some reason, I'm not sure I ever figured this out, as you can see by the fact the code just ends. But when I first did this, including the gradient, with the strategy that sort of both Tom and I were thinking about, I ended up having the minimum be here, which is obviously not actually the minimum along this line or along a sort of fattened version of that line. And I don't know, I think I didn't actually figure out what was happening there. But if I take out the gradient, for some reason it does seem to have worked, and it did find the minimum actually being here where it looks like the actual minimum is. So to some degree this seems to have worked, but there's still a little bit of an unexplained mystery here as to why the optimization was failing in this case there. And that might have to do with starting values. It might have been that if we left the gradient in, and so I was starting at 3, 3.1, so somewhere up here. It might have been that if I chose a different starting value that was sort of more in this region, or more in this region, I guess, then I might have still been able to include the gradient there. So I'm not totally sure what's going on with that, but that does give sort of a flavor of some of those sorts of things you can do and some of those sorts of tricks that you might try in these situations. Or if you were really trying to do this sort of heavy duty, like I said, you may want to go to either Python or MATLAB in that case. Okay, any questions or comments?
So if you don't provide its gradient, then you're going to use the numerical derivative?
Yeah, presumably it's doing a numerical, calculated numerical derivative here. In fact, let's see what it says here. Right, so it says gradient of f or null, see below. Oh, I see. Okay, so the gradient function, it's not quite what my answer was or what you were expecting. The gradient must be supplied except with method Nelder-Mead. It should take arguments matching those of f and return a vector containing gradient. So I think, actually, okay, so that actually, now that, I'm glad you asked that question. I think that explains what I was doing here. So I'm not sure what we'd have to look into it and see what the default method. So the other thing about this is it's using optim behind the scenes. So for any given one of these approximations to the inequality constraint, it is then just doing a regular call to optim behind the scenes for each one of these iterations as we relax this. So we could do that using Nelder-Mead. We could use it doing BFGS, all of the various approaches to using optim that we've talked about. So presumably what's going on here is in the second one, it's using Nelder-Mead, and that does seem to converge to the optimum. I'm not sure let's see, does it say what the default is here? Oh, okay, so it does say. So it says method if is.null of grad, Nelder-Mead, otherwise it uses BFGS. Okay, so it looks like, so this was using BFGS. It seemed like it had some problems there. This was using Nelder-Mead, and it seemed like it did do a better job there. So that sort of reinforces my point from earlier on this unit about trying different optimization methods is a good strategy to take. Okay, so let's switch over to the integration and differentiation unit. So the basic idea here is differentiation will come up a lot in optimization. You're seeing it in needing to use it in the projects. Integration comes up in terms of computing expected values, or sometimes we may want to try and marginalize over like a random effect in a given statistical model, and so it can be useful to be able to do integrals numerically. So those are some of the contexts in which this is useful. So let's start with numerical differentiation. There's sort of not all that much to this conceptually, but it's useful to think about because it ties back in with some of the numerical issues that we've already talked about quite a bit earlier on, and that seem to keep arising as we've seen just this morning. So if we think about derivatives, well, how do we get f prime of x? Well, if we just go back to our early days in calculus, well, we're just going to take a limit where we take f of x plus some small increment h minus f of x, and we divide by the increment h. So we could think of approximating this numerically as just saying, okay, I'll just take a small h, I'll use this as my approximation to the derivative, and that should give me an estimate of what the derivative is. And then, of course, if we're trying to approximate something where we're taking a limit, well, presumably we want to just take h smaller and smaller and smaller and smaller. And that's going to give us a more and more and more accurate estimate of what the actual derivative is. Okay, so now, as in a lot of the cases this semester, or at least recently in the last few weeks, if we're thinking about doing a calculation, we have to think, okay, I'm not actually doing this calculation as a mathematical calculation. I'm doing the calculation as a calculation on a computer. And I know that there are going to be things that could go wrong in terms of actually doing things accurately when I'm in that situation. So if I think about this and think about what are the calculations I have to actually do here, suppose that I let h be smaller and smaller and smaller. What are the things that could go wrong in the steps involved in doing this calculation? So can you think about what could go wrong in doing this? Yeah, Brad?
If h is too small, then
Okay, so we've already talked about one definition of machine epsilon being if you add a very, very small number to x, you might get x back if the number that you add is too small. So if this is less than machine epsilon, x plus h is just going to be x, and we're going to get f of x minus f of x, which is just going to give us back 0, and is obviously not a good estimate of the derivative. Right? So we certainly know that we can't let h be any smaller than machine epsilon. Right? Well, let's let h be small, but not that small. think about what about this? Well, we're going to take f of x plus h minus f of x. So now suppose h is maybe just a little bit bigger than machine epsilon, 1 times 10 to the minus 15 or something like that. Any thoughts about what can happen then?
Yeah, if the function makes them closer together rather than farther apart, you could get something less than what
Okay, so you could also get, well, you could get differences that are really small. Maybe another way of putting that is, let's suppose we let h be really small, and f of x plus h and f of x are very close to being the same number. So that's essentially what you were saying, right? Okay. So let's suppose f of x plus h is, I don't know, whatever, 1.23, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, etc., etc. And now we get f of x, and they're very, very close together, right? So suppose that's 1.2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, and now something other than 4. So let's suppose this is a 6, and then something else here, right? So now if we think about subtracting these, well, I'm basically subtracting off all of these numbers up through here, and those are just going to disappear. So this is catastrophic cancellation all over again from the numerical unit, that all of these are going to disappear. This is going to be our difference, and we know we can only represent this accurately up to 16 digits, so I don't know exactly where 16 is here, but let's suppose this is 16. We have, some small number of accurate digits here, plus a whole bunch of garbage here, right? And now basically what's the role of h? Well, h is basically now sort of scaling this back up to put it back on the original scale of sort of the function and the original scale that we were working on. So now h scales this back up. Well, we've lost all of our most of our digits of accuracy, and now we're working with a derivative. We're working with an estimate of the derivative based on the difference, where this portion of the difference here, so this is going to be accurate. This portion of the difference is going to be inaccurate, and we don't have very much accuracy in our estimate of what the derivative is because of the cancellation issue. So this suggests we can't, even if we had h being bigger than machine epsilon, there might be some issues if we let it get too small in terms of how accurately we can represent the difference in the number. We could take this even further and think about what happens in terms of h. We then have to divide by h. That might introduce some additional inaccuracy in terms of doing that calculation as well. So that basically tells us we don't want h to be too small, but we also don't want it to be too big. Okay, so we'll come back to that in a second and actually see an explicit example of that. Okay, so one way to get more accuracy, apart from letting h get smaller and smaller and smaller, is just to use a better estimate of what the derivative is. So as you might expect, this is a first difference, and this is called a central difference. If we take f of x and go h in one direction and h in the other direction, and use the estimate of the gradient from those two evaluations of f. So not surprisingly, since we're, you can sort of think about this intuitively just from a picture, I have some, if I go plus h here, this is going to be, I don't know if I can actually draw this very well, but if I take basically 2 points around this, that's going to be more likely to be essentially very close to being the actual gradient than if I go if I just step in one direction from the point x at which I'm interested in the derivative. So that's the idea of doing the central difference here as an estimate. One downside to doing this is oftentimes we'll have already calculated f of x in the process of doing whatever our calculations are, and so this would require only one more calculation of the function relative to if we've already gotten this in hand, whereas this would require 2 calculations of the function. So sometimes if you're thinking about this, that might be something to consider. But you can work out basically that the order of the error in the forward difference is order of h, and the order of the error in the second difference is order of h squared. And this is a case where h is going to be small, so smaller than 1, so we want higher powers of h in terms of our estimate of what the order of magnitude of the error is. Okay, and then you can play this out by, if you wanted a second derivative, so if you're doing calculations of Hessians, then you can basically just take the first derivative of the actual gradient function, and then if you plug in the estimates of the first derivative from getting a numerical estimate, well then you get that an estimate of the second derivative either this quantity if we're thinking about forward differences, or this quantity if we're thinking about second differences. So we have easy formulas for estimating both first and second derivatives. If you want to think about doing directional derivatives in any particular direction in a higher dimensional space, then there's something analogous here that you could look at on your own. But that's sort of basically what you need to do to calculate a numerical estimate of the derivative. Okay, so in terms of going back to the numerical issues, folks have done a lot of work in thinking about what are good values to use for h. And so basically we want to think about taking h to be scaling by the magnitude of x, basically the square root of chain epsilon. That's been suggested as a good rule of thumb. But then other people, when they're thinking about trying to estimate second derivatives, then suggest actually use that you use the cube root of machine epsilon instead of the square root of machine epsilon. So those are the sorts of things that you'll see is that the relative size of h should be roughly around either the square root or the cube root of machine epsilon. So the idea is here is I just want to show an example to sort of emphasize this point, and we'll just see an actual example in practice, and we'll see that this notion of either using the square root or the cube root actually works out pretty well for this particular example. So okay, so what I'm going to do here is I'm going to try lots of different values of h. So I'm going to try h everywhere from 10 to the minus 1 down to 10 to the minus 15. So basically almost all the way down to machine epsilon, starting from 0.1, which is obviously not a very small h. And I'm going to do it for a function where I can actually calculate what the derivative is and what the second derivative is analytically, and then be able to evaluate that quite precisely in R. So I'm going to use the log of the gamma function. And the first derivative of that can be calculated using an R function called digamma, and the second derivatives can be calculated using a function called trigamma. So based on these, I can get really accurate estimates of what the actual derivatives are. So this is obviously just a toy example, because if I could do this to calculate derivatives, I wouldn't need to get the numerical derivative. So here, those are my values. Those are going to be my values. Those are my values for pretty high precision estimates of what the first and second derivatives are at x equals to 1/2 there. And now I'm just going to do first and second forward difference and central difference for the first and second derivative as numerical estimates. So that's what I'm doing here. I'm doing plus and minus h, plus and minus 2 times h for components of the second derivative calculation. And then I'm doing the forward difference and the second difference for both the first derivative and the second derivative. So I'm just implementing all of that stuff that I had in the notes. And I'm doing it in a vectorized fashion for all of those different values of h that I strung out, 0.1, 0.01, 0.001, et cetera, et cetera. Okay, and now I can create basically a table of the values for the different values of h. And remember that, did I write it down? Okay, so let's just write this down for comparison's sake on the board. So I've got that the accurate estimate of the first derivative is minus 1.96 351003. And then for the second one, it's 4.93 48022. So this is f prime, this is f double prime for x equals 1/2. Okay, so here are the different values of h, ranging from 0.01 down to 1 times 10 to the minus 15, disappearing off the screen here. And this is the first forward difference, and so I'm looking for 1.96351003. And I can see I get there right around 1 times 10 to the 8th and 1 times 10 to the minus 9th. So this is basically my best estimate from doing the forward difference with different values of h. So it looks like right around square root of machine epsilon is more or less the best value. And you'll notice as I get h getting smaller than that, I actually get less and less accurate estimates of the derivative. So this is actually playing out in practice here. If I look at the first derivative, but at the central difference, which is the order of h squared error instead of the order of h error, I can see that I get an accurate estimate as soon as I get to 1 times 10 to the minus 5 or 1 times 10 to the minus 6. So I don't need to make h as small to get an accurate estimate with the central difference as I do with the forward difference. And in fact, given that point is 0.003 is the accurate answer, this actually never quite gets there even at the best value, whereas I actually get to the best value for this whole range of different h's with the central difference. Okay, so any questions so far? And then if I look at the second difference, that's 4.9348. So I can look here, okay, 4.9346, 4.93. So basically the best I can do is these two values here, which are only accurate up to about 3 decimal places. And this is at about 1 times 10 to the minus 5 or 1 times 10 to the minus 6. So right around the cube root of machine epsilon. And I'm not actually getting a very good accurate answer in the second derivative. And now this, so that was the second numerical second derivative with the forward difference approach. And this is with the central difference approach. So here I can see, okay, 4.9348, 4.934802. I'm looking for 0.22, so 0.23. So it looks like right around in here is my best estimate. And I've got, it looks like about 6 decimal places of accuracy here. So I get a few more decimal places of accuracy here compared to here. And in this case, it looks like something right around h or right around here is giving me a pretty good estimate. So this is a sort of a nice illustration that what folks have worked out as a rule of thumb of how to choose h actually does play out, as we can see here in this example where we actually know what the right answer is. And you can see crazy things start happening as h gets really small. So if you went into this naively and said, okay, maybe even I understand the idea of machine epsilon, so I know that my h needs to be bigger than machine epsilon, but let me get really close to it, and then that's going to give me a really accurate answer. So let's try it. 1 times 10 to the minus 14 and 1 times 10 to the minus 15. You don't do terribly for the first derivative, although you're not doing great compared to what we know to be the accurate answer. But all of a sudden, you basically have things blowing up here when you're doing the second derivative, and you get just crazy nonsensical values because of how the numerical inaccuracies carry forward through the calculations. Okay, so if you want to do this in R, you could, code that up yourself. There's not too much involved in doing that. You can also use the function numeric deriv, which is in the numderiv package. And basically what you need to do is give it an R expression and then tell it what are you differentiating with respect to. And that will, in this case, so if we did that for this L gamma function, you can see that it gives us an estimate of the derivative that's minus 1.96351001. So a little bit off down here in the 8th decimal place, but essentially as accurate as what we were getting doing it ourselves. Okay, so I think that's all I want to say about that. If you want to do symbolic differentiation, so this is a good idea if you're trying to come up with the actual analytic derivative, but you don't actually want to do it by hand either because you're lazy or for a good reason because all of us, at least most of us, make mistakes when we try and take derivatives by hand. R will actually do a little, well, we've actually already seen this in the, I forget what example it was, one of the examples in the optimization unit. I used this deriv function to actually do symbolic derivatives so that I could then plug those into an optimization calculation, into a numeric optimization. So if we give it an expression and tell it what we're differentiating with respect to, it will give us back a new expression that has the expression that will compute the gradient for us. So that's a nice thing to be able to make use of. And here I'm just showing a little bit of trickery with R that says, okay, I could actually start with a function, and then I could take the derivative. I need to give deriv an expression, so let me take the body of the function f. So this is a handy way to pull out just the expression that's the body and the body of the function. Take the derivative of that. This new body function is going to give me back a function that calculates both the value of the original value of the function and the gradient and potentially the Hessian, depending on so I used derivative 3. So I could actually create a new function f and plug this new body of that function back in as the body of that function. So just a little bit of sort of machinations with manipulating functions in R. And that would allow me to then, without having to do the derivatives by hand, create a new function that gives me back gradient and Hessian information. So there are some limitations to exactly what terms in a given expression R can handle in terms of differentiation. So for example, I don't think it can handle if you have a sum in the expression. So if you actually want to do this in more complicated examples, then using software like Mathematica or Maple is a good strategy. So we have Mathematica in the SCF, and you can get it through campus. And so if you're in Mathematica, you can do things like give me the symbolic derivative with this function capital D of this expression with respect to x, or the second derivative with respect to this second derivative with respect to x, or the mixed partial derivative with respect to x and y, et cetera, et cetera. And so that if you're wanting to get analytic derivatives, then this is a good way to do that. Okay, so any questions before I talk a little bit about integration? Okay, so the main point I want to make here is basically to contrast Monte Carlo integration, which we already saw in the simulation unit, with doing it numerically in a fashion called quadrature, which is sort of the terminology that people use for talking about numerical integration. So basically the sort of the big picture story here is that if you're in low dimensions, then using quadrature methods is a really good strategy compared to using Monte Carlo integration. But as you get to higher and higher dimensions, and in this case high dimensions doesn't actually mean all that big, like it means like 3 or 4 or 5 or 6, then quadrature is really not a good approach because it doesn't scale well with dimension, as we'll see in a little bit. So in that case, doing a Monte Carlo estimate of an integral is actually a better strategy as you go to higher dimensions. So that's sort of the basic story here and the main thing that I want you guys to take away from this. So let's just lead. I want to lead off with a little bit of a sort of a motivating example. And again, it's sort of just a toy example where we know the right answer and we can see how accurate an answer we get using R's implementation of quadrature versus using a Monte Carlo estimate. So this is just going to be a one-dimensional integral. So suppose I wanted to integrate sine of x from 0 to 2 pi. So if you do this, just mathematically, you'll see that that integral is just 2, so we know the right answer is 2. And we can think about doing this either using quadrature in R, and that's going to amount to using the integrate function, or we can think about doing it as a Monte Carlo expectation. But we know that in terms of Monte Carlo expectations, what do we get? Well, we get some expected value. So we get some. From the simulation unit, we know we can get a Monte Carlo estimate for the expected value under some distribution f for some function h of x. And so that's just going to be integral h of x, f of x, dx. So if I want to do a Monte Carlo estimate of this integral here, then I need to put it in a form that looks like this, where I have some density function here on the right side. Okay. So in this case, I could do that by saying, well, okay, if I want to integrate from 0 to, is it pi, I guess? Yeah. The sine function, well, I could think about that as h of x being the sine function, and then f of x being a uniform density from 0 to pi. So I'm just going to introduce the density by manipulation. Okay, so if I want to have f of x here, well, I know that the uniform density from 0 to pi is just 1 over pi. So I just need to multiply by 1 over pi and then multiply by pi to make sure that this works out. So I'm just going to introduce the uniform density here and then introduce pi here to cancel out with the uniform density that I introduced. So I've just rewritten this as an expectation under f, where f is uniform from 0 to pi, of this new function pi times sine of x. So oftentimes you can do these sorts of tricks when you're in these kinds of situations and you want to get something to look like an expected value. Okay, so if I actually do this in R, Okay, so I can use this method called quadrature, which is implemented in the integrate function. And what does it say? Well, it says that the integral is 2 with an absolute error less than 2 times 10 to the minus 14. So that sounds pretty good. I think what it's doing here when it comes up to the errors, it basically uses a higher order and a lower order approximation to the integral, and it's able to sort of bound the error based on doing that, although I haven't looked into the details in any depth. And you can see this is quite quick. It turns out that it can't even actually calculate how fast it was. Okay, so what about if I use a Monte Carlo estimate of the integral? Okay, so I'm going to just draw random uniforms from the interval 0 to pi, and then I'm going to take the average of sine of x, where x is drawn from random uniform 0 to pi, and multiply by pi. So this is just my Monte Carlo implementation of estimating an integral. And I can do that with different values of n and see how long it takes and see what I get. Okay, so if I do it with 1,000 samples drawn from a uniform from 0 to pi, then I get that my estimate of the integral is 2.001, so it's accurate up to basically 2 decimal places here. And this was really quick. This was also so fast that R couldn't even tell me how long it took. It was under whatever the resolution with which it's doing the timing. But that wasn't all that accurate an estimate. So what if I just start increasing the number of samples that I use for my Monte Carlo average? So if I use 10,000, for example, well, now I get that the answer is 1.991. That doesn't actually look like it helped all that much in terms of getting a more accurate estimate. Presumably, there's just some random variation here in what points actually drawn and how close the actual answer is to the true answer. But now I'm starting to get times that I can actually see how much time it takes. But maybe I'm not all that satisfied with that amount of accuracy. So now I'm going to use draw a million samples for my Monte Carlo estimate. And now I'm starting to get somewhat more accurate answers. Although actually this is even not, if I sort of think about rounding here, this is even not all that much more accurate than what I had up there. But now I've got something that takes 0.1 seconds. So you can see it's starting to get to be negligible time to actually do this calculation. Okay, any questions at this point? Okay, so let's talk a little bit about methods for these estimating these integrals numerically. Okay, so the basic strategy in a lot of different numerical integration methods can actually be rewritten in this form, is to write the integral. So suppose I'm interested in the integral of f of x from over some integral a to b, is basically to break it up into pieces and write this as a sum of integrals over these smaller pieces from xi to xi plus 1. And then the idea is, if I look at this term that's inside the sum, I'm going to then approximate that integral inside the sum by another summation over some aij values and f of x star ij. So these things are called nodes, and basically exactly what we use for that and exactly what the values of a or j are correspond to different methods for doing the numerical approximation. So you can think about sort of what choices we might make here in doing this approximation. Well, I have to choose, sort of how many of these chunks to use in breaking up the integral. And I have to choose exactly what the points are at which I start and stop each of the intervals. And then I need to choose how do I actually approximate the integral within any given one of the intervals. So there are a variety of different choices that have to be made in doing this. Okay, so there are a bunch of terms here. Again, this is sort of like some of the other things we've seen that, sort of all the famous mathematicians from 200 or 300 years ago, their names are on, various combinations of these methods. So Newton was involved in this, sort of not surprisingly. So what goes by the name of Newton-Cotes quadrature is basically that sort of generic strategy that I just showed you a second ago, but where you have equal length intervals. So we're going to take h being the interval length here, and that's going to be from b to a, so the limits over which we're doing the integration, divided by the number of intervals that we choose to divide up the integral into. And then we're going to we're going to basically do an approximation to the integral within each of those small intervals, and we'll do different kinds of polynomial approximations. Okay, so this sort of goes back to initial stages of when we first saw calculus. So suppose I want to integrate this function from a to b, and let me just divide this up into a certain number of equally spaced intervals. And okay, well, I'm just going to evaluate f at each of the beginning points of the interval. And so one approximation I can do is just a Riemann type integral, where I'm just going to add up the area of the boxes here. Right, so now I'm just going to add up the area of each of the boxes, and that's going to serve as my approximation. So if I just if I rewrite that in this form here, well, that just basically amounts to taking a constant approximation to the function in each interval and then multiplying by the difference xi plus 1 minus xi, so just the length of the interval. So this serves as that aij value. There's just one of them. And this serves as my f evaluated at these nodes, except in this case, the node is just the initial point in the interval. So this is just rewriting, sort of integrals, ways of doing integrals that we've already seen before from calculus in this form up here. You can also think about the trapezoid rule. So instead of doing straight across, we're now going to replace this with doing these trapezoids here. And if I do that, I can rewrite the trapezoid rule in this form here, and that also takes the form of some aij value, a sum over aij. You could rewrite this as a sum of aij values times f of x at these nodes x star, where here these would be the two x star values. And then, so this is now, I said before that Newton-Cotes is using a polynomial approximation in each interval. So we've seen that the Riemann approximation is just using a constant approximation. The trapezoid rule is just using a linear approximation to the function in each interval. Simpson's rule is just using a quadratic approximation in each interval. So this is going to amount to getting higher and higher accuracy by using a better and better approximation to what the function is in each of the intervals. So if you work through what Simpson's rule looks like, well, it looks like this, and you could rewrite this also in terms of the aij's and the f of the x stars and the f of x at these node values. So we'll generally, we can quantify the error of doing these different numerical approximations to the integral in terms of h, the size of the interval. And so if you do the trapezoidal rule, that's going to give an order of h squared, and Simpson's rule gives an order of h to the fourth. So it's basically squaring the error, which in this case is, or squaring it's basically going as the square. I think I'll just stop there. You know what I mean. This is better than this because h is going to be small. Okay, so let me quit there, and we'll finish up integration on Wednesday, and then go into some of the graphic stuff.